Hello, my name is Jeff Messier. I'm a professor of electrical and computer engineering at the Schulich School of Engineering at the University of Calgary, and this is my module on the probability of bit error. Communication systems designers are always concerned about determining the reliability of their system. So we know that when we send our analog waveforms through our analog channels, that they will get distorted due to noise, interference, and sometimes due to the channel itself. And the result, even with a properly and carefully designed detector, will always be a certain number of bit errors at the output of our receivers. And these errors are random, right? Because the mechanisms that cause the signal distortion are also random. And so the way that we quantify the reliability of a physical layer communication system is through probability of bit error or bit error rate. Although, to be strictly correct, probability of bit error is how we refer to reliability estimates that we derive using analytical expressions or equations. And bit error rate, it refers more to the experimental measurement of the reliability of a system by sending a bunch of bits through it and then counting the number of errors. In this module, we are going to focus on determining probability of bit error using equations or analytical expressions rather than simulation. And it's common for students and even very experienced people to say, really, the art of determining probability of bit error expressions has become a lot less important now that simulations are so good, right? We can use MATLAB or some other tool to very quickly put together a detailed and accurate simulation of a communication system and determine probability of bit error through that simulation. And so a lot of people question the value of calculating probability of bit error using equations. And the reason why we still do it and the reason why it's still important is that, a well-formed equation can give us a lot more information than a simulation. So if you generate a bit error rate curve through the use of a simulation, it's fine, you get your result. But just looking at that curve, you really have no idea what system parameters affect the shape of the curve and how sensitive your system is to different variations in the system. Whereas if you look at an equation, as long as the equation is not too complex, you can see the equation, you can look at all the variables that go into the equation, and very quickly you can, just through inspection, tell what the most important system parameters are that affect the reliability of your particular system. So for example, if channel gain is squared, then you know that it's, it has a fairly large effect as opposed to another parameter maybe that is multiplied by a very small constant or perhaps taken to the square root. And so, and in addition, simulations can take a long time to run. So if you want to, for example, simulate a bit error rate value of 10 to the minus 6, it's important that you simulate long enough to get a statistically significant number of errors. The rule of thumb is usually you need to count 100 errors, although in my experience it's often, if you want a nice smooth curve, maybe a bit closer to 1,000 errors. But even for 100, that means if you want to simulate a bit error rate of 10 to the minus 6, you need to simulate 100 million bits on average. And again, your equation, as long as it's not too complicated, you can get that bit error rate value almost immediately. And so there is a lot of value still to being able to find probability of bit error equations, which is why we still do focus on them and why I've dedicated a module to it. Now, deriving error expressions is a real art, particularly for complicated systems with complicated channels, wireless channels, and whole, academic papers are dedicated to deriving probability of error for a particular case or a particular type of channel. what we're going to do in this module is we're going to take a relatively simple approach just to introduce you to this area. We will be looking at maximum likelihood detection for the additive white Gaussian noise channel only, and the examples that we work through will be just a few of the most common types of modulation schemes. But you should be aware that there are lots of other techniques out there for deriving probability of error, and I'm only going to show you one of them just by way of an introduction. Okay, so to start off our discussion, what I'm going to do is derive a general expression for the probability of error for vector-based additive white Gaussian noise detection, which is what we looked at in our previous detection module. And so let's say our received signal vector R is equal to some signal vector SC plus N. And the subscript C indicates that this is the correct vector. And the correct vector SC is chosen over an error vector SE as long as the squared distance between the received vector and the correct vector is less than the squared distance between the received vector and the error vector. So when an error occurs, the following becomes true. The distance from the received signal vector to the correct one is now larger than the square distance between the received vector and the error vector. And so if we plug in the equation for R, so if we plug in this equation up here into this expression, then the left-hand side just becomes n squared because the SC's cancel, and the right-hand side is n plus SC minus SE. Now, if we expand out this squared norm and manipulate it a little bit, we get the final expression where our Gaussian noise vector n, weighted by the cross product with the transpose of the difference between our two error vectors, has to be less than the squared distance between the two vectors, the negative of the squared distance between the two vectors divided by 2. So if we focus specifically on the left-hand side of this equation first, n is a zero mean additive white Gaussian noise vector, and we weight the noise contents or the noise terms in that vector with the transpose of the difference between SC and SE. When you scale or weight Gaussian noise vectors, you adjust their standard deviation, or you change their standard deviation. And so we end up, if we look at the distribution after this vector multiplication, the distribution of the noise terms will still be zero mean, but the standard deviation, or sorry, the variance, rather than being n naught divided by 2, is n naught divided by 2 scaled by the square of the distance. And that's just, again, a result of this multiplication here. So the probability of error then, if we use the expression from the previous slide, the probability of error is then just the probability that this term is less than this term. And the term on the right-hand side of this relationship is constant. SC minus SE is a constant. And the term on the left-hand side of the left-hand side, or less than sign, is Gaussian distributed. And so we can then use the Q function to determine the probability, and that Q function expression is written here. We've got the squared distance between those two vectors appearing on the numerator and the denominator, so we can do some canceling. And then the final probability of error is then just the Q function, with the argument of the Q function being the distance between the two vectors divided by the standard deviation of the noise, basically, or the slightly scaled standard deviation of the noise. And so this is a nice compact expression, and it's an intuitive expression in the sense that The greater the distance between these two vectors, the smaller this probability is going to be, right? Because you start your integral further out on that Gaussian tail. And that's what we would expect, right? The greater distance we have between two vectors, the less likely we are to confuse them at the detector. So our result on the previous slide was interesting, but not particularly useful in the sense that it still is. We still need to do some extra work in order to nail down an expression for the overall reliability of our system. So what we had on the last slide was an expression for the probability of confusing two specific error vectors, confusing two specific signal vectors in the presence of Gaussian noise. However, a constellation is made up of a whole bunch of different signal vectors, and so we've got a whole bunch of different distances that we need to take into account. Now, it would be technically possible to basically just calculate the distance between each signal vector and then include that in a large chain of Q function terms to come up with an exact expression for probability of error. However, again, remember that one of the motivations for coming up with an analytical expression for probability of error in the first place is that we would like simple expressions that allow us to quickly determine what parameters affect system performance. And so in the spirit of that, what we're going to do on this slide is simplify the error expression a little bit. And so while there are a large number of distances, we can take a conservative or pessimistic approach, and we could say, well, let's assume that every single point in our constellation is separated by the minimum possible distance, d min. When we do this, this gives us an upper bound on the probability of error. Why is it an upper bound? It's because it's pessimistic, right? There are actually some points that are further away and the probability of error won't be as large as we're assuming. But upper bounds are often desirable in system design because they're a conservative estimate. They're, I guess, the safe, using them is kind of a safe approach, quote unquote. And we know that if our system performance is okay for an upper bound expression, then it's going to be okay for sure because our actual performance will be a little bit lower than that. So here's our simplified expression. So you'll notice in our Q function on the numerator, we assume that d min has, we replace the distance between SC and SE with just the minimum distance on our signal constellation. And then we multiply the Q function expression by m minus 1. Why do we do that? Well, there are m possible transmitted signal vectors, but one of them is the right one, right? And so the overall probability of symbol error is the probability that we make an error with the first incorrect signal vector plus the probability we make an error with the second incorrect signal vector, the third incorrect signal vector, and so on. The total number of incorrect signal vectors are m minus 1, and so that's why we multiply them. Incidentally, we're able to add these probabilities because the error events are mutually exclusive, right? You can't make a mistake with one vector and another vector at exactly the same time. So this is an expression for the overall probability of symbol error. Why we say symbol is because this is the probability that we mistake two signal vectors. Which we refer to as symbols. However, the metric that we're usually looking for is the probability of bit error, or the bit error rate. And so to achieve probability of bit error, we make another approximation. And if we assume that gray coding is used, that means that the signal vectors that are closest together differ by at most 1 bit if it's properly done. And so when we make a symbol error, that corresponds to just a single bit error. And so the probability of bit error is approximately equal to the probability of symbol error divided by the number of bits per symbol. And again, that's an approximation because we assume that one symbol error corresponds to one bit error. However, one symbol carries n bits. And just to clarify this with an example, let's consider the case of 8 PSK, where the number of bits per symbol n is equal to 3. If gray coding is used, that means that only when we make a symbol error, only 1/3 of only 1 in 3 of the bits will be bad when we make a symbol error, because one bit is incorrect, but because gray coding is used, the other 2 bits are the same between neighboring symbols. And so the probability of bit error is the probability of symbol error multiplied by 1/3. And so what I want to do now is I want to take this, this upper bound expression, and on the next few slides, use it to derive the probability of bit error for a series of common modulation schemes, BPSK, QPSK, and 16 QAM. And then at the end of the module, we'll compare these probability of error on a probability of error versus signal to noise ratio graph, and we'll talk about some of the things that we learn about system performance because of those plots. So to start off with binary PAM or binary phase shift keying, BPSK, we have 2 signal vectors equal to some amplitude A multiplied by the root of the pulse shape energy and the negative amplitude. The distance between these 2 signal vectors is equal to, or the square root of 4a squared EG, or the square root of 4 times the energy per bit, because the energy per bit is equal to, in this case, the energy per symbol, which is a squared EG. And the probability of symbol error and the probability of bit error are equal because 1 bit equals 1 symbol. And so if we can take our distance expression, put it in our numerator, do a bit of canceling, and then the probability of bit error for binary PAM or BPSK is equal to the Q function, and the argument to the Q function is the square root of 2 times EB over N naught. Now, you'll notice that we were able to get this expression in terms of EB over N naught, and at the end of the matched filter module, we talked about how EB over N naught is sort of the common way of expressing signal to noise ratio. And so we always want to be able to get our sort of end expression for probability of error in terms of EB over N naught, because typically when we plot the results of our work, we plot what are called bit error rate curves or probability of error curves. And on the y-axis, we have the probability of bit error, usually on a log scale. On the x-axis, we have EB over N naught, usually in dB, and the curve looks something like that. And so in our next slides also, we're going to be trying to get our final expression in terms of EB over N naught. So as for QPSK, we know that there are 4 signal points in the QPSK constellation, and the signal vectors for those points are given here. Now, the way that we determine bit error rate for QPSK is to note that QPSK is really just 2 BPSK modulators, each one working on a different basis function. And we can see that when we look at the constellation diagram. So, for example, if we consider first of all the basis function f1, the cosine basis function, we note that when we look at the gray code bit mapping, when the first bit is 1, we are always on the right-hand side of the y-axis. And when the first bit is 0, we are always on the left-hand side of the y-axis. Similarly, if we look at the second bit, when the second bit is 0, we're always above the x-axis. And when the second bit is 1, we're always below the x-axis. And so basically, we can think of the BPSK modulators as the first modulator corresponding to the first bit, which determines the x-coordinate of the signal vector, and the second modulator corresponds to the second bit, which determines the y-coordinate of the signal vector. And so we can then analyze the performance of these two orthogonal BPSK modulators using minimum distance. And so dmin is the same on, or in both the x direction and the y direction. So dmin is the same for both of the modulators. And that minimum distance is given by this expression. And when we substitute that into the generic probability of error expression, we get a final result that is equivalent to conventional BPSK. The third type of modulation scheme we're going to consider is 16 QAM. And here's a constellation diagram for 16 QAM. And it is obviously a lot more complicated than QPSK and BPSK. But with a square QAM constellation, you can actually make a quick kind of approximation that really simplifies your probability of error derivation. So if you notice this, or if you take a look at this signal constellation, basically you can make a square constellation by choosing one of 4 values on the x-axis and one of 4 values on the y-axis. And so really, square QAM is equivalent to 4 airy PAM, where you've got one PAM modulator working along the first basis function along your x-axis, and one PAM modulator working along the y-axis. And so when we derive the probability of error for 16 QAM, we instead basically just sort of say, okay, well, this is equivalent to 2 PAM modulators kind of working in parallel, each one working on an orthogonal basis function. The performance of these 2 PAM modulators are going to be exactly the same. And the overall bit error rate performance for 16 QAM is exactly the same thing as the performance for 4 airy PAM. And so when we do our minimum distance calculation, rather than looking at 16 signal vectors, we only look at 4. And these signal vectors have the amplitude values that, it's kind of hard to see probably on the video because it's compressed, but these signal vector values are the same values along the x and the y axis. And the minimum distance then is equal to twice the amplitude times the square root of the energy per pulse. And so when we look at the probability of bit error expression, we plug in our minimum distance here. Because we're assuming 4 airy PAM, we've got 2 bits per symbol. And so we multiply by 1 over 2. And this 2 is actually a typo. This should be m minus 1, which in this case equals 3. So now the final step of the derivation is to convert the argument to the Q function in something expressed in terms of EB over N naught. And for this part of the derivation, we really do need to take the full constellation into account. And so the average energy per symbol, ES, for the overall constellation is 1/4 times this long expression, or 10 times a squared EG. The average energy per bit is just the energy per symbol divided by 4, because it's 16 QAM. So we get 5 over 2 a squared EG. And then if we plug in this expression for EB into the Q function argument, we get this final expression for the overall probability of bit error for 16 QAM. Okay, this final slide shows a plot of the probability of error, or the bit error rate, versus EB over N naught for BPSK, QPSK, and 16 QAM, both for the analytical expressions, the theoretical expressions that we derived in this module, as well as a MATLAB simulation that I did for the actual signal constellations. Just a few words about the plot itself. On the y-axis is shown on a log scale. This is always done when plotting probability of bit error. And the x-axis shows signal-to-noise ratio in dB, so it's effectively a log scale as well. The theoretical results are shown by solid lines. Those are plots of the equations that we derived in the previous slides. And then the points, the circles show the simulated BPSK, the X's show the simulated QPSK, and then the squares show the simulated QAM. And the first thing you'll notice is that the simulated results agree perfectly with the theoretical results, both for BPSK and QPSK. And as we expected from the equations, for a given EB over N naught, let's say 7 dB, we get exactly the same bit error rate, 10 to the minus 3, for both BPSK and QPSK. And so that indicates that, first of all, our approximation or our analytical expressions are very good. And also, it highlights the points that with QPSK, you can get double the throughput for the same bit error rate when expressed in terms of EB over N naught. However, if I had showed signal-to-noise ratio in terms of energy per symbol over N naught, QPSK would require twice the signal-to-noise ratio. If we look at the QAM results, the first thing you'll notice is that the squares don't quite fall on top of the solid line. And again, that's because the expression we derived was an upper bound. So it ended up being exact for the BPSK and QPSK scenarios, but it is an upper bound for the 16 QAM scenario. And as a result, the bit error rate predicted by the equation is slightly higher than the simulation, but it's not too bad. We would consider this a fairly tight bound. If you consider the horizontal distance between the point and the curve, it looks like it's maybe 1/4 of a dB, which is not too bad. The next thing you'll notice, though, is that bit error rate is noticeably higher or noticeably worse for the same value of EB over N naught. So for a signal-to-noise ratio of 7, we get a bit error rate that is about 0.5 times 10 to the minus 2. So what's going on here is that if we think about the transition from BPSK to QPSK, we got a doubling in our throughput for the same reliability for EB over N naught. The reason why we were able to get such a significant improvement is because we used the second orthogonal basis function, basically. However, when we go from QPSK to 16 QAM, again, a doubling in throughput, just like the BPSK to QPSK transition, but we no longer introduced any additional signaling dimensions, right? We just had to pack our signal constellation with more points. And because of that, even when we express it in terms of EB over N naught, we see a performance degradation. So for the same signal-to-noise ratio per bit, we just cannot get the same reliability with 16 QAM that we could with QPSK. And this highlights one of the fundamental trade-offs in communications that's very, very important always for systems designers to remember. There is this constant throughput, reliability, power trade-off. So if we wanted, if we had a QPSK system and we wanted to double its throughput with using 16 QAM, either we would have to settle for lower reliability and go up in this vertical direction, or if we wanted the same reliability, what we would have to do is increase our signal-to-noise ratio to 11 dB. So we would have to increase our energy per bit or the amount of energy we invested in transmitting each bit, we would have to increase it by 4 dB in order to get the same reliability at twice the throughput.